Okay, so this is a Raspberry Pi, and like other computers, the CPU of the Raspberry Pi needs to be kept cool during operation in order to increase the lifespan, but also to increase the performance of the CPU. Now, the goal of this project is to try to control the CPU temperature using a heatsink and a fan. Now, the fan I'm going to be using is just a spare 120 millimeter 12-volt case fan that I had lying around that I hooked up to an external power supply and the Raspberry Pi to try to control the temperature. And I did this with this circuit that you see here that I came up with. And what it's really doing is taking this 3.3 volt pulse width modulated signal from the Raspberry Pi to drive a MOSFET, which converts that 3.3 volt signal to a 12 volt signal in order to drive the fan. Now this is the setup that I was working with the fan just about 10 centimeters above the Raspberry Pi. You can see the heatsink on the CPU poking out right there. Um, and yeah, that's kind of what I was working with. Now, to model this system, I started with a simple energy balance. And there's three important things here. There's our controlled variable, which is the temperature. There's our heat transfer coefficient, which is going to be a function of the fan speed. And then there's the heat being generated by the CPU, which is going to be a function of the CPU load. That's going to be our disturbance variable right there, where the fan speed is going to be our manipulated variable. Now, using a sum of resistances model to calculate U, or the heat transfer coefficient, we get that this equation here where it's a function of the fan speed to some m power, and the heat being generated is going to be a function, just a linear function of the CPU load. And that reduces to this energy balance here below. And doing some impulse testing, we can fit that model to the data and come up with these parameters up here at the top. And you can see that it's actually quite a good fit to the data. Now what I also did is I also fit an FOPDT model to this data, which really was not a very good fit at all, but what was able to do is take that FOPDT model and those parameters there and use them to uh, calculate some initial PID tuning parameters. And I did that using ITAE correlations, specifically for disturbance control, and came up with these PID tuning parameters right there. And I was able to use that in a simulation. I used some simulated sort of randomized CPU load down there at the bottom in orange. But what you see here at the top is that the controller performance is actually really good in this simulation. We have about 100 seconds for the rise time and pretty negligible overshoot. And so, in simulation, this is looking really good. Unfortunately, it's not quite as good when we actually implement this. What you can see here is that there seems to be quite a lot of noise in the temperature measurement. Now, there is some noise. It's not the best temperature probe, but what you can also notice is that the CPU temperature in red up above tracks very closely with the changes in the CPU load down in the bottom graph here. Um, and unfortunately, the Raspberry Pi was not able to sample and recalculate everything it needed to fast enough to be able to really keep up with these disturbances. And so the time scale of the temperature response to the disturbance, to the change in the CPU load, is actually much shorter than the time scale that the controller is able to respond on, which gives rise to some of these fluctuations that we see in the graph. So that's really not ideal. Unfortunately, I was not able to get the Raspberry Pi to measure things fast enough to really be able to overcome that. But what we do see here, which is encouraging, is that if you disregard that first 100 seconds, that the CPU temperature, the controller is actually able to keep it in a fairly good range, plus or minus about 2 or 3 degrees from the set point, um, pretty much at all times under moderate CPU loads, under about 70%. what we do see here is the beginning first 100 seconds of that graph, and also down here, right around 500 seconds, is that when the CPU load gets above about 70%, 75%, that the CPU is generating too much heat for the fan to reliably dissipate. You can see here that the fan's at max speed 100%, but the temperature is still climbing, which is unfortunate. That means that there's some hardware changes or configuration changes that we need to take place to be able to deal with these large disturbances. Um, but potentially, if you were able to make those hardware changes, then um, you could actually be able to control the temperature much better than I was able to. But ultimately, though, the controller performance, plus or minus 3 degrees of the set point, is actually quite good, um, and uh, and completely adequate, I think, for this application. But what do we learn from this? Well, we learn that it um, actually is quite hard to accurately control a process when there's a whole lot of disturbances, especially if you have large disturbances, like in this case. Um, and if you do have disturbances like that, you need to make sure that your hardware is actually able to deal with those disturbances. If you have disturbances that are too large, then your system won't be able to handle it, and you'll really have some problems in if it's something that's maybe more important than a CPU on a Raspberry Pi. Ultimately, this because of these fluctuations, because of the disturbances, it may not actually be that effective, or really the right way to try to control this. What computer manufacturers have been doing for years is just setting a fan curve, and instead of trying to control the temperature of the CPU to a set point, they'll just try to keep the CPU temperature low and within a reasonable range. Um, and ultimately, that's probably a better way to go about this. Although, as we uh, as we see here, it can be plausible to try to control the CPU temperature in this manner.